Hi everyone, Dr. Burns here, and we have reached our final chapter in COR141 for this semester, and we're looking at population means this time. So the last two chapters we spent a lot of time talking about sampling distributions for population proportions. Now we're going to get into sampling distributions for population means. The concepts are very, very similar. So hopefully the two ideas kind of come together for you because the general concepts are the same, but the context is a little bit different in that now we're using means. So in this first section, I just want to get into looking at some terminology and notations, and then we'll use it going forward. If we want to talk about the accuracy and the precision for our sample mean and how well that uses, or how well that estimates rather, the population mean, I want to remind you about a couple of these notations that we're going to see as we do that. Remember, mu was equal to the population mean that we generally need to estimate. I usually can't go out and measure every single height of every single woman in America, for example. So I have to estimate what that is. Remember, X bar is the sample mean. So when I pull a sample from the population and I calculate the mean for that sample, that's X bar. A couple other reminders. Remember, the population mean is a parameter, whereas the sample mean is a statistic. Sigma is your population standard deviation, and so that is also a parameter. And then S is your sample standard deviation. And since that comes from the sample, that would be a statistic. So this is just a little refresher. We talked about these earlier back in chapter 7. So there's three key features that we want to keep in mind when we are using the sample mean to make an inference about the population mean. The first is accuracy. The sample mean is going to be unbiased when estimating the population mean. On average, that sample mean will be the same as the population mean, or close to it, I should say, so long as we are selecting random samples again. That's been the theme, I feel like, and it continues even with this topic. The next is precision. So the precision for the sample mean depends on the variability in the population. And as always, the larger the sample size, the more observations we collect, the better our standard error becomes, the smaller, I should say, our standard error becomes, so the more precise our sample becomes because we have a smaller standard error, right? Larger samples lead to smaller standard errors. And then finally, we want to look at the sampling distribution, just like we've previously looked at. The sampling distribution can be thought of as the distribution of all possible sample means that we would get if we were to draw repeated samples over and over and over and over again of a certain size from our population. Same exact idea as what we talked about in the previous sections. The only difference now is that we're looking at means instead of proportions. That's the only change. The standard deviation for the sampling distribution, of course, as always, is called the standard error, right? Standard error. And as I mentioned right here, as the sample size increases, the standard error gets smaller. But just like it did with proportions, the mean stays the same. The mean does not change. A couple other key points here that I want to mention. As I said above, if we're looking at random samples, then the sample mean is an unbiased estimate for the population mean. And the standard error for that sample mean. Now, here's a new formula for standard error because we're not talking about proportions anymore. So make sure you've got this in your notes somewhere. The standard error formula now is going to change slightly. It's going to become sigma, so the population standard deviation, divided by the square root of n. And that's going to be the standard error when we're looking at a sampling distribution for means. And don't forget also that n is our sample size. Here, let's write that down. So n is the sample size, and sigma is the standard deviation for the population. If we know it, we're going to use sigma. Let's look at a quick example. A student has a large digital music library. The mean length of the songs in the entire library is 258 seconds with a standard deviation of 87. The student creates a playlist that contains 30 randomly selected songs. Is the mean value of 258 a parameter or a statistic? So this is the mean for the entire population of songs. So that would mean it's a parameter, and the symbol we would use is mu. So mu equals 258. What should the student expect the average song length to be on the playlist? So she should expect the average length to be 258 seconds. Could it be higher or could it be lower? Yes, but it should be around 258 seconds. What is the standard error going to be for her playlist? So the standard error, that's our new formula from up here. It's going to be sigma divided by the square root of n. So sigma divided by square root of n. Now what is sigma? Sigma is the standard deviation for her music library. So the population standard deviation for the library was 87 seconds. So it's going to be 87. And then n is the number of songs that we've selected. Our sample size then is 30. So the square root of 30. So let's see what that gives us. And I am getting about 15.88 seconds. So the standard error for her sampling distribution should be about 15.88 seconds. Now, would a playlist of 50 songs have a standard error that is greater than or less than your answer? So now we're changing our n, our sample size, to 50. Well, think about what that's going to do to the standard error. If my sample size is larger, that's going to reduce the standard error because now you're going to be dividing by a larger number. So it's going to be less than, because the standard error will get smaller in the equation, in the formula, however you want to say it. But it's because you're dividing by a larger number. And we can calculate that. You can pause the video and see for yourself, but it will be a slightly smaller number than the 15.88. Let's do one more example. The average income in the District of Columbia in 2013 was $76,000 per person for that year. That was longer than the average for any state. Suppose the standard deviation of 35,000, the standard deviation is 35,000 and the distribution is right skewed, as income levels often are. We've mentioned that before. We take a random sample of 100 residents. So before I get too into this, let me write some things down. The average income for everybody in the district was 76,000. That means mu is 76,000. Try to get in the habit for these. So go ahead and write some of this down when you get it. The standard deviation for the entire district was 35,000. So that would be sigma. N is my sample size. So that's going to be 100 residents. What value should we expect for our sample mean? Well, we expect our sample mean to have an average income of 76,000. Why? Because we took a random sample. Could it be higher? Yes. Could it be lower? Yes. But it should be fairly close to that number. What is the standard error for our sample mean? That's our formula. So that's going to be 35,000. So sigma divided by the square root of n, which is 100. So that's going to be 35,000 divided by 10, lose one of these zeros, and we get standard error of 3,500. Now, let me show you what this looks like in the Art of Stat website. All right, let me do a quick demonstration for what this would look like. So we've got a right-skewed population because we're looking at income levels, and they told us it was right-skewed. My population mean is 76,000 and my standard deviation is 35,000. My sample size is 100. So the data for the population is up here. Here's what the population would look like. Let's draw one sample and just kind of get a quick idea. The mean for my sample is 75,344, fairly close to 76,000, so that's not too far off. And the standard deviation for the sample is 30,293, but we want to know the standard error for the sampling distribution. So I need to draw more samples to see that. I'm going to run a few samples here. I'm going to go ahead and do a bunch. I'm going to do 100 samples to get a really good feel for what this is going to look like. And take a look so you can see what we have here. I'm going to just keep on pulling samples of 100 at a time. And you'll notice that my mean is around 76,000. My standard deviation is 3372. Remember we said it should be around 3,500. There's 3,422. It's dancing around a little bit, but it's fairly close to that 3,500 that we would have expected for our standard error. And we'll do some more practice with this in class tomorrow. I love this website. I think it's a really good way to show you how these sampling distributions look. And we'll talk more in the next lesson about what the shape of this is going to eventually look like. So I'll see you in class.